Let's do an example with the robot trying to get back home. So as we said before, the robot can only go down or right, and the robot cannot go through the X obstacles. As you can see, these X's, they're not allowed to go through it, and you cannot go out of bounds. So I'll use this example to show you how we will be using recursion to solve backtracking problems. In here, in this problem, what are the smaller subproblems we're trying to solve? There are two subproblems. One, if the robot started in one square to the right, and then the other one, the other subproblem is if the robot started one square below the original square. So we could think of it as a whole problem itself. Imagine if we did not start here and the robot started here, then it's a new problem. Also this one, if it started at one step below, it's also a new problem. Now let's assume that this problem has already been solved. So how would we solve our whole problem, the original problem, while assuming that these subproblems have already been solved? So in our case, the solution will be a list of letters, which is either R for right or D for down, and then the solution basically tells you the path the robot needs to go in order to reach its home, right? So for example, if you just look at it here, the actual solution should be D, D, R, R, D, R, right? So how do we get this solution? Well, like I said, let's assume that we have already solved this subproblem for when the robot is on the right. And then all we need to do is add the letter R to our solution because we're going right. So now the solution has R in it. And then whatever is the answer to subproblem, because we're assuming that we have already solved the subproblem, and we just append it, and then that would be our solution. However, as you can see, it's actually impossible because once you're on this cell, there is no way you can get to your home without either going through an X obstacle or without going out of bounds. And as I said before, you cannot go left or up. The only directions you can go are right and down. So because there are no possible solution for that, then what do? We are going to backtrack. So we're going to take our R out because this subproblem is impossible. So we are going to backtrack, take out our R, and then this time we will try D. So if we did D, then this subproblem already has a solution. And the solution is the list D, R, R, D, R. As you can see, the red line, it shows you how you get to the end. So for this problem, the answer is D, R, R, D, R. And what did we say we had to do? We just had to append our D, because we're going down, to the solution that we will have. So basically, that's the solution. So as you can see, it's quite easy if you have the subproblems already solved. The only difference between this and the recursion problems we did is that we backtracked. So the backtracking happened when we put R into our solution, but we realized that is wrong, and then we took R out of the solution, and then we added D instead of R, and then we continued. It's very possible also that you don't have any solution. It's not R nor D, like you're just stuck. Like for example, if the robot was here on this cell, then no matter if you go right or down, you will not be able to solve the problem, and that would just return none. However, here we do have a solution, and the solution of this subproblem is D, R, R, D, R, and then we add to this solution our original direction, which is down. As you can see, the orange D, and we added the orange D here. And then now we have our full solution here. Okay, now I'll show you how this function actually built up the list. So if I go step by step what actually happened, you'll see it in here. So for example, when I went to the right, I actually called the function. I recursively call my own function, but this time we set the position to be 1 to the right. And then I added this R to the solution. And then I would go right again, and then I would add an R to the solution again. So as you can see, I went to the right, and then I added R to the solution. And then here, you could go right, but what's going to happen is that if you go right, it will be a non-acceptable state because you're out of bound. So instead, I recursed the other way, going down. And then I added D to my solution. And then now, as you can see, you're stuck because no matter if I go down or right, it will be out of bounds, or I would encounter an X obstacle. So my solution is here, but it should be kind of stuck here. And what do you do now? You backtrack. So I remove the D because I know that this position is not the right position. And then we backtrack again. So you remember here, we couldn't go right, so we backtrack. And then remember here, we could go down, but that's also not good because there's an X obstacle, so we backtrack. We keep backtracking and we take off these R to the solutions. All right, and we backtrack again because we realize that no matter what, we cannot complete the puzzle or the maze if we are on this square, which is one right to the original position. So what do? We finish backtracking this whole path, and then now we have the second path, which is going down. And then I'll kind of do it a lot faster. I could have gone right, and then you realize it couldn't work, so we went down. We try to go down, it doesn't work. Okay, so we go right instead. And then we go right again. I don't have space, so I'm gonna erase these other nodes. And then if we try to go right, we cannot because there's an obstacle here. So we're gonna backtrack and then go down instead. And then we're gonna go right. And then finally, we have reached our destination. And then this is our solution, DDRRDR. To summarize, what were our base cases and what were our recursive cases? So in the next lesson, we'll actually code it out. But for now, let's think about it. Let's think through it first, because it's always good to think about your problem, think about how you're going to solve it before actually writing the solution. So what were the base cases? So there are 3 base cases, right? So imagine if the robot is already home. For example, imagine if my subproblem was this one. This one has already been solved because the robot is already home. So if the robot is already home, then I just return the current solution that we have, all right, which is this one, because we built up the solution. But then if the robot is out of bounds, meaning out of the grid, that shouldn't work either. It's not a valid solution. So we just return no solution because no matter what, that's wrong. And then if the robot is on X obstacle, for example, like in this case, if you went right, then they are out of bounds. So then because it's out of bounds, then there's no solution. So these are base cases. These are the super easy case where you don't even need recursion. And then what are the recursive cases? Well, we kind of talked about it, and I could actually show you a graph that shows you all the possible ways you can traverse this maze. So this is what we actually call a decision tree. And you'll learn a lot more about trees in the future, and this is kind of like a good sneak peek. So what does this tree represent? So like I said, it's a decision tree. Every time we go up, it means we go right. As you can see, the robot went to the right. And then every time we go down, the robot goes down. So why are there 2 children for each parent node? So you'll learn the vocabulary now. A parent node means the node that starts pointing at the 2 other node. Each square here is a node. This node has 2 children because it has 2 nodes under it. There are 2 children because the robot can only go right or down. So the robot only has 2 choices to make. So as you can see, whenever I go into a base case, because this is actually a base case, then I either do an X or a circle. For example, this base case is the same base case as is the robot on an X obstacle. So there's no solution, so I put an X on it. And then this one, as you can see here on the top corner, this one is a different base case. This one is the robot out of bounds. As you can see, it was on the top right corner, but then it chose to go to the right, but then it went out of bounds. So that's also an X. And then the last base case is when the robot is already home, which is right here. All right, and then if we go back to the original problem, what happened is if we go to the right, we have solved this subproblem, which is this one. Solve the subproblem if the robot goes right, add right to your solution, right? So we added right to our solution, and then now our solution looked like R plus whatever this subproblem gives us. However, once we go deeper into the recursion, we realize that none of these outcomes are good. We cannot actually solve this problem. So what happened is we backtrack all the way to our original problem, and instead we're gonna go right. And then once we go right, we do the same thing. We solve this subproblem. And then after we go deep into the recursion, we actually found one node that is complete, which is ending up into the base case. And then because we do have a solution, we come back from the recursion and gives us the solution dr. And then all we have to do is add the direction that we went to, which is direction down, to our solution, like so. And then you could see it right here. Solve for the subproblem if the robot goes down, which is what we did. We solved this problem, giving us the ddrr or whatever. And then we add down to your solution, which is the orange D that we added to our solution. And then what happened is return a solution if the subproblem is solvable, and it was solvable. So now we just return this. So what happened was, again, if we went to the right, we did not return the solution because the subproblem is not solvable. So instead, we backtracked. So what would happen if we had an X here, right here? Then none of these would work. So we would backtrack, and then we would realize that there is just no solution available. And then if none of these solutions work, if you go to the right or down, then you just return none because there are no solutions to your problem. All right, so I hope that was clear. In the next lesson, we will be coding this. And now that we have the framework, it would be a lot easier to code. All right, see you next time.